Hello students, today we are going to discuss the numericals based on electrostatics. Okay, so first numerical is two charges of magnitude minus 4q and plus 2q are located at a point 2a, 0 and 5a, 0 respectively. What is electric flux due to charges through a sphere of radius 4a with center at origin? So definitely we have to determine the electric flux due to charges through a sphere of radius 4a. Okay, so there is a one sphere whose radius is 4a with center at origin. Okay, so basically if I consider this is radius of sphere, okay, so radius of sphere is 4a. Now from this diagram, distance OX1, this is O, distance OX1 is 2a and distance OX2 is 5a. Clear? So this is x2, OX2 is 5a. 5a means actually center plus a, that is 5a. It is actually provided in the diagram and radius is 4a. It is provided. So radius is 4a and this distance is 5a and distance OX is 2a. So Gaussian surface of radius 4a and charge, now listen here important. This charge minus 4q and plus 2q are located at point 2a, 0 and 5a, 0. Now 5a, 0, okay, 5a, 0 and 2a, 0. So definitely if you consider, there is a one important point, 5a, 0 is the this point, 5a, 0 and 2a, 0. So this is actually 2a, 0. Now listen here, minus 4q is at 2a, 0, means minus 4q is the charge inside the Gaussian sphere, inside the closed surface, but this charge is outside the sphere. So if this is a sphere and this is a Gaussian sphere, we know that. So Gaussian sphere, if I try to draw the Gaussian sphere, then this is a Gaussian sphere. So we have to consider the charge inside the actual sphere, which is now in this case minus 4q. That's why flux is equal to q enclosed by epsilon naught, which is equal to minus 4q upon epsilon naught. Clear? Because as per Gauss theorem, flux is equal to q enclosed upon epsilon naught. Here enclosed charge is minus 4q upon epsilon naught. Clear? Okay. So answer is minus 4q upon epsilon naught. Next question. A 6 microfarad capacitor is charged by 300 volt. It is then disconnected from supply and connected to another uncharged 3 microfarad capacitor. How much electrostatic energy of first capacitor lost in the form of heat due to radiations? Okay, so a 6 microfarad capacitor, 6 microfarad capacitor is charged by 300 volt. So whenever we are charging a 6 microfarad capacitor by 300 volt, how much charge is developed on that capacitor? It is C1 times V, because Q is equal to CV. So Q is C1 times V. What is the value of C1? 6 into 10 raised to minus 6 into V is 300. So answer is 18 into 10 raised to minus 4 coulombs. Okay, 18 into 10 raised to minus 4 coulombs. So charge developed on the capacitor is 18 into 10 raised to minus 4 coulombs. Okay, now energy U is equal to actually half into Q times V. So which is equal to half into Q is actually how much Q? 18 into 10 raised to minus 4 into V is 300. So how much energy stored? 27 into 10 raised to minus 2 joules. So energy stored is 27 into 10 raised to minus 2 joules. Now what they are asking you, suppose there is one uncharged capacitor 3 microfarad. Okay, now that particular 6 microfarad capacitor which is charged by the supply of 300 volt, and then the charged capacitor of 6 microfarad is disconnected and it is connected to 3 microfarad capacitor. So like this, suppose this is a capacitor, first I charge this, okay, so C is equal to how much? 6 microfarad, and how much? This is 300 volt. Once this capacitor is charged, now I have removed this capacitor. So this is a charged capacitor connected to uncharged capacitor. This is a and connected to uncharged capacitor of 3 microfarad. Okay, so this is a 3 microfarad capacitor. So what happens? There is a redistribution of charges take place, so that in the charge on this capacitor is equal to charge on second capacitor. So Q is equal to Q dash. So what is the charge stored on the first capacitor? V times C1 is equal to V dash times C1 plus C2, because now these two capacitors are parallel, and in parallel equivalent capacitance is C1 plus C2. That's why actually it is C1 plus C2 into V dash. V dash is the common potential actually, because in parallel the potential is same across each capacitor. That's why this is very important step here. Q is equal to Q dash. So Q is actually Vc1 is equal to V dash C1 plus C2. So V dash is equal to Vc1 upon C1 plus C2. So V is 300, C1 is 6 into 10 raised to minus 6 upon 6 plus 3, that is 9 into 10 raised to minus 6. So common potential actually is 200 volt. Okay, common potential is 200 volt. So this is a very crucial step in this problem. Okay, you have to equate this. Why? Because there is a redistribution of charges take place across each capacitor. So that initial charge is equal to charge developed on second capacitor. Initial charge on first capacitor is V times C1, but final charge is actually now two capacitors are parallel. So overall capacitor is C1 plus C2 times common potential V, and you are getting common potential as 200 volt. So when you connect the first charge capacitor to the second capacitor which is uncharged, then the first capacitor which is charged will provide the charges to the second capacitor until the second capacitor attains the potential of 200 volts. So that is called common potential, because both the capacitors have same potential. Okay, so now we have common potential 200 volt. Now second, how much energy is stored by the second capacitor? Second capacitor energy stored is U2 is half Q V dash. So half Q is 18 into 10 raised to minus 4 into 200, that is 18 into 10 raised to minus 2 joules. It is the energy stored by the second capacitor, and energy stored by the first capacitor is how much? That is energy stored by the first capacitor is actually 80, that is 27 into 10 raised to minus 2 joules. So it is the energy stored by the first capacitor. Energy stored by the second capacitor 18 into 10 raised to minus 2 joules. It means provided energy is 27 and stored energy is 18. So remaining 9 joule energy is lost. So that's why energy lost is U1 minus U2, which is equal to 9 into 10 raised to minus 2 joules, or it is 90 millijoules is the energy lost in this process, because total supplied energy from the first capacitor is 27 into 10 raised to minus 2 joules, but second capacitor stores only 18 into 10 raised to minus 2 joules. So how much energy is lost? That is 9 into 10 raised to minus 2 joules energy is lost. Clear? Okay. Now next question. 125 small liquid drops, each carrying charge of 0.5 microcoulombs and each of diameter 0.1 meter, form a bigger drop. So there are small drops, okay, and each drop carries a charge of 0.5 microcoulomb. Such 125 charge drops combine together to form a big drop of the and each drop has a diameter of 0.1 meter. Okay, so calculate the potential at the surface of big drop. Now listen here. Radius of bigger drop, that is capital R, and small r is the radius of smaller drop. So radius of bigger drop capital R is equal to small r into n raised to 1 by 3. So that capital R is equal to small r, what is the diameter? 0.1 meter, which is 0.05 meter radius, into, actually you have to remember this. Okay, this is called as combination of charge drops. So in combination of charge drops, radius of larger drop is equal to radius of smaller drop into n raised to 1 by 3, where n is the number of smaller drops. So capital R is equal to 0.05 125 raised to 1 by 3, because 125 small drops are there. So this is 0.05 into 5, which is 25 into 10 raised to minus 2. Now we have obtained the radius of big drop. Now we obtain radius of bigger drop. We know the charge on that particular drop. We can easily calculate the potential using formula, because that drop is a point charge. So V is equal to 1 upon 4 pi epsilon naught Q by R. 1 upon 4 pi epsilon naught is 9 into 10 raised to 9 into charge is 0.5 into 10 raised to minus 6 upon 25 into 10 raised to minus 2. So what is the potential? How much? 9 by 5 into 10 raised to 9 by 5 into 10 raised to 2 into 10 raised to 2. So final answer is potential on the surface of bigger drop is 1.8 into 10 raised to 4 volt. So what is the potential? 1.8 into 10 raised to 4 volt. Clear? Okay. Next, problem number 4. The dipole moment of water molecule is 6.3 into 10 raised to minus 30 coulomb meter. A water sample contains 10 raised to 21 molecules whose dipole moment oriented in the field of 2.5 into 10 raised to 5 Newton per coulomb. Calculate the work to be done to rotate the dipole from theta 1 is equal to 0 to theta 2 is equal to 90 degrees. Now listen here, initially dipole is aligned parallel to the field. I have to rotate it through an angle of 90 degrees. We know that in this process there is some work done. That work done is actually equal to PE into bracket cos theta 1 minus cos theta 2. Now PE into bracket cos theta 1 is 0, so cos 0 minus theta 2 90, cos 90. So cos 0 is 1 and cos 90 is 0. So that's why work done is equal to PE only. Now P is how much? 6.3 into 10 raised to minus 30 and E is how much? 2.5 into 10 raised to 5. So work done is equal to 1.57 into 10 raised to minus 24 joules. 1.57 into 10 raised to minus 24 joules. Now listen here. Basically this is the work done for one molecule. How many molecules are there? 10 raised to 21 molecules. So total work done is 10 raised to 21 into W1. So that is 10 raised to 21 into 1.575 into 10 raised to minus 24. So how much total work done is to be required? 1.575 into 10 raised to minus 3 joules. So definitely you have to use direct formula here, P into bracket cos theta 1 minus cos theta 2. But that is the work done for a single molecule. We have to calculate it for 10 raised to 21 molecules. So multiply it with 10 raised to 21 to get the answer as 1.575 into 10 raised to minus 3 joules. So in this way I discussed 4 problems, okay, in which first problem is related with the basic Gauss theorem. Second problem was related with redistribution of charges, energy storage. Third problem was combination of charge drops, and fourth problem was with work done for the dipole, okay, that is P into bracket cos theta 1 minus cos theta 2. Now we are going to discuss remaining problems. Now we are going to discuss next problems. A charge 6 microcoulomb is placed at the origin and another charge minus 5 microcoulomb is placed on y-axis at position a 0,6 meter. Calculate the total electric potential at point P whose coordinate are 8, 0. Calculate the work done to bring proton from infinity to point P. So a charge 6 microcoulomb is placed at origin and another charge minus 5 microcoulomb is placed on y-axis. So this is a minus 5 microcoulomb. 6 microcoulomb is at origin. Calculate total electric potential at point P whose coordinates are 8, 0. So this is point 8, 0. And second, calculate work done to bring proton from infinity to point P. From infinity to point P we have to bring proton. Now total potential at point P using principle of superposition, Q1 by 4 pi epsilon naught R1 plus Q2 by 4 pi epsilon naught R2. So 1 upon 4 pi epsilon naught is 9 into 10 raised to 9 into bracket. Now listen, Q1 is minus 5 upon 8 this distance from origin plus 6 upon 8, okay. That's why total answer is 2.25 into 10 raised to 3 volt. Now listen here, actually this is a formula for point charge in which the point P is at a distance of 8 meters from origin. Then work done to bring the basically proton from infinity to point P is actually Q1 Q by 4 pi epsilon naught into bracket 1 upon infinity minus 1 upon R1 plus Q2 Q by 4 pi epsilon naught into bracket 1 upon infinity minus 1 upon R2. So which is equal to minus Q times V. So actually this is minus Q times V because 1 upon infinity is 0, okay. So you are getting actually V means 1 upon 4 pi epsilon naught Q by Q1 by R1 minus Q2 by R2. Now Q is actually 1.6 into 10 raised to minus 19 into V is 2.25 into 10 raised to 3, which we have calculated. So answer for this question is minus 3.6 into 10 raised to minus 16 joules. So minus 3.6 into 10 raised to minus 16 joules is the work which is required to bring the proton from infinity to point P. Next question. In a parallel plate, this is actually very important question. In a parallel plate capacitor with air between the plate, each plate has area 6 into 10 raised to minus 3 meter square. The separation between the plates is 2 millimeter. Calculate the capacitance, charge on capacitor if supply is 100 volt. How would capacitance would be affected if mica sheet of 2 mm thick and K is equal to 2 is inserted? So definitely we have to calculate C, Q and new value of Q if some material, dielectric medium with dielectric constant 2 and thickness 2 mm is inserted between the plates. Now you know that formula for parallel plate capacitor, C is equal to A epsilon naught K by D. Now epsilon naught is 8.85 into 10 raised to minus 12 into area is 6 into 10 raised to minus 3 upon D is 2 into 10 raised to minus 3, which is equal to 2.655 into 10 raised to minus 11 farad or 26.55 picofarad. Clear? So C is 2.655 into 10 raised to minus 11 or 26.55 picofarad, because 10 raised to minus 12 means pico. So Q is equal to C times V. What is the value of C? 2.655 into 10 raised to minus 11 into V is 100. So this is 2.655 into 10 raised to minus 9 coulombs, because Q is equal to C times V and C is equal to A epsilon naught K by D. Now new charge, if we insert the dielectric with K is equal to 2 and thickness 2 mm between the plate, is Q dash is actually K times Q. Okay, now K is actually 6 into original Q is 2.655 into 10 raised to minus 9. So Q dash is 1.593 into 10 raised to minus 8 coulombs. But important point is, they have mentioned कि supply voltage is not disconnected and you inserted the mica sheet. If you disconnected the supply and if you inserted the mica sheet, then original charge is equal to new charge. There is no any change in the charge, but supply is still connected. That's why there is charge becomes K times Q. Clear? Okay. Last problem. Okay. These are the two arrangements and we have to calculate the equivalent capacitances in these two arrangements. Listen here. Actually, there are 3 layers of medium. This is the first layer of medium with K1 is 1, that is dielectric constant. Second medium has dielectric constant K2 3 and third medium has dielectric constant 6. So this is called a distance division method. The distance has been divided. So for this C1, C2, C3 are three capacitors are in parallel. So C1 is A epsilon naught K1 by D1, that is D by 3. C2 is A epsilon naught K2 upon D by 3. C3 is A epsilon naught K3 upon D by 3. So 1 upon C is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. So if you substitute 1 upon C1, C2, C3, then C equivalent is 2A epsilon naught upon D. Okay, 2A epsilon naught upon D. Okay, now this is the final answer for this setup. For this setup, actually it is a combination. Okay, so whenever there is a distance division, series is a combination of capacitors. So these 3 capacitors are in series. And you know, see, for series combination we have discussed it in the theory. Now listen here, this K2 and K3, here distance is divided D by 2, D by 2. So these 2 capacitors C2 and C3 are in series and overall capacitance of 2 and 3 is in parallel with first K1. Okay, so first we have to solve for this. So in this case 1 upon CS is 1 upon C1 plus 1 upon C2, this, which is A epsilon naught K3 by D by 2 into A epsilon naught 6 by D by 2 upon A epsilon naught 3 by D by 2 plus A epsilon naught 6 by D by 2, which is equal to 2A epsilon naught by D. So if you solve this parallel series combination of capacitors, then equivalent capacitance is 2A epsilon naught upon D. Clear? Okay. Now if this capacitor and these capacitors now are in parallel, so definitely for parallel, what is the total formula? CT is equal to C1 plus C2. So C1 is 2A epsilon naught by D plus actually A1 A epsilon naught K1 by D1. Clear? A1 K epsilon naught K by D1, that is A by 2. So in this way you are getting total is actually here actually 2 because A by 2. Now it is area division. Listen here, in the parallel arrangement area is divided. So for these two, this and this distance is divided, so both the capacitances are in series and that overall capacitance is parallel with this, so area is divided. So whenever area is divided, parallel arrangement. When the distance is divided, series arrangement. So now once you solve this series arrangement, so this capacitor is parallel with this. So that's why it's 2A epsilon naught by D plus 2A epsilon naught by D, that is 4A epsilon naught by D. So here after substituting it is 4A epsilon naught by D. So answer for first question is 2A epsilon naught by D. Answer for second question is 4A epsilon naught by D. So for second case, there is a combination of two cases, that is first case is distance division, second case is area division. In distance division, both capacitors are in series. In area division, capacitors are in parallel. Clear? So in this way, we have completed the numerical session of electrostatics. Okay, so you have to go through the revision lecture in which I completed all the formulas, and later on you go through this particular numerical session, then try to solve some important problems by your own, so that it becomes easier for you to revise the content. Okay, and I completed each and every problem here itself, so there is no necessity, only you have to learn whatever I have taught you. Okay, and you have to revise the formulas. That formulas also I have provided you in the revision lecture, that is a objective revision. Okay, so for each chapter, after completing each lecture, once the chapter is finished, then I have provided all quick revision sessions, in which first part was the theoretical revision and part 2 was dedicated to your numerical, that is your formula revision. So once you watch that particular lecture, then you go through this lecture and solve all the problems. Okay, so and you try to revise all the content, try to prepare the notes, so that every chapter can be 100% accurate and there will not be any problem while preparing. Clear? So in this way I stop here. We will meet in the next session of problem solving, in which we will discuss the problems on current electricity. Okay, so thank you.